All right, I have a seed question. So, and it's really, and we're gonna have a modeling session next as well, which is we can, oh, well, actually, I'm gonna go, you go ahead. All right. This is a question for Leah. So you were doing the time dependent, were you launching a CME in that? No. So yeah, that was my question. Do you have plans for launching a CME into the time dependent background?
Yes.
Oh, sorry. Yeah, we need so we need the lapels. Just unmute them both for now. Okay, go ahead.
Yes. So right now, still. Okay. Yes, so what you saw was only solar wind, even though some structures sometimes could be mistaken as CMEs, and this is what I think is exceptional. We can see structural structures in the solar wind itself, which is amazing, and we need to understand what exactly we see there. Right now, Elena is working with CMEs, although in a steady state background, but we do have plans in the frame of another proposal to incorporate the CMEs into the time-dependent solar wind background.
Okay, thank you. And also a reminder, folks, with the lavaliers, hold them just a little bit to the right of your mouth when you talk. Go ahead, or left, your choice.
Hi, Leah, Becca from Muse. I'm curious about your magnetic field boundary condition. Are you using a potential field extrapolation similar to,
Yes, so we're using the WSA model to drive the boundary conditions at 0.1 AU. That means that we do use the BFSS model and the Schatten currency model together.
And so then I guess the follow-up is that I see that you can take into account at least the larger scale flux emergences at the time cadences. Do you have any plans to include, for example, smaller scale flux emergence or even tighten your time cadences?
Yes, well, that's a good suggestion indeed that we are actually discussing all the time how we can improve this, right? And right now we are more focused on the magnetograms itself. The time cadence, you mean for the magnetograms, like how frequently we're going to update. We're currently updating up to 2 hours because we're using long adapt magnetograms, and this is the time cadence that going adapt magnetograms are being provided to the public. But if we use any other kind of magnetograms from another observatory, they may come in 1 hour cadence and so on. But it's not only the cadence that is to blame for that. It's also the way sometimes you may interpolate, or as I said, the WSA sensitivity. But we are working on that.
Excellent. Congratulations. That's great work.
Thank you.
Thanks. This question is really for everybody, but it was stimulated with, I think, Pratik's cartoon of the CME being much crazier than one might think from our simple models. With stereo, we saw CMEs evolving and getting squished by the wind and so forth. With PUNCH, we've been anticipating that, but that cartoon was just really wild. It was all over the place. Nothing like the kind of round flux ropes that we model now. How do each of you think we need to prepare for these more complicated overall flux ropes? Not just with interior structure, but maybe a more contorted three-dimensional structure.
And exactly don't have the idea how to do it from the remote sensing. Maybe trying to do a complementary study with multiple spacecraft and simulation can give us some idea about how much deformation is happening on it.
Yeah, I think this is a common issue where we have these sort of idealized semi-analytic solutions because it's tractable, and real life doesn't do that. And so we run into this in a bunch of different parts of the field. And really, I think the only good approach is to solve this problem is better, more fundamental physics and simulation and better observations. And PUNCH is going to give us one of those things. So we need to, on the simulation side, sort of catch up and run, not just potential field models and idealized analytic flux ropes, but more higher resolution and more physics simulations to catch up to the better observations that will be taken.
I agree, no, I agree. Let's go.
Just put them all on.
Yes, I agree with what Matt said. High resolution, I think it's very important, but before studying and analyzing the more complex structures, we really need to make sure what we say in the simpler structures. And PUNCH will help, of course.
Yeah, we are actually doing very similar things like you. We are studying the distortions of the CME. And what we are usually trying to see how first it looks in the 3D and then integrate it so that it mimics basically the observations. And I think this is the way to compare it with PUNCH data.
Thank you. It's hard to underestimate, hard to overestimate, excuse me, whatever. It's easy to understate how important simulations are going to be. I'm reminded very much of Anna Malonyshenko's work. She's not here today, but this business about the highest entropy case in the corona is not small loops, but very complicated structures. And I've been thinking in the back of my head, we're going to find that here. And I think you've all said that in various ways today.
Hi, this is Russ Howard again. So I'm following actually on what we just heard, that the CMEs really are complex. They are what we're seeing from WISPR on Solar Probe is our CMEs running into each other that we had not anticipated. We wrote a paper, Gopal Swami and I wrote a paper many years ago on the radio emission that he detected from two CMEs that were colliding. That was one out of decades. But what we're seeing now is that in the first tensile radii, the things they're piling up, they're hitting each other very, very frequently and distorting each other. And so the question that I was originally thinking is, if you have two CMEs, both coming from the same region, they have the same polarity. The second one, the faster one usually, does it just simply go through, or does it just, what we see is it distorting, which is not what the magnetic field would say. And so what's happening?
From what I have seen in my simulations, if the two CMEs have the same polarity and same parallelity, then the reconnection will be happening in the back and the front of the CME, the interaction region. Additionally, it also depends on the momentum of the two CMEs. If the second CME is bigger or fatter, have more density and more speed, and if the gravity and polarity are same, then even it can penetrate inside the first CME, and it can partially go in front of the CME as well.
So, yeah, that's the usual picture. That has been the picture, but that's not what we're seeing, I believe. I believe what we're seeing, in fact, is the CMEs getting squished and elongated quite a bit in the latitudinal direction, and not penetrating, and that's
Okay. Yeah. Maybe the parallelity, because for the reconnection or the cannibalism to happen, we should have the right configuration of the free lines also. If there are opposite free lines, so there will be like pressing the first CME, it will become thinner and elongated, but it won't be reconnecting and it won't be done. That could be a possibility.
I just want to add that, not my work, but Andreas Weiss at NASA Goddard has been doing a lot of work on in-situ measurements of very heterogeneous CMEs.
That's right. And we're seeing that. Yeah, I think it's happening lower, but it could also be happening in inflammatory space.
I think this is one of the places where spatial, like 2D spatial measurements like PUNCH can really complement in-situ measurements.
Yeah, absolutely.
And just comment that, oh, sorry, do you want to say? Go ahead. Oh, you switched off. There you go.
I speak now. So I just want to say that, actually, we should not try to generalize too much because you have, different events, interacting in different way. We have one of, the cases when my PhD student was studying, we have, interplanetary, CMEs interacting with each other. And, the particle accelerated bouncing in between the two of them before the full interaction happened. And when the full interaction happened, they were really like completely messed up. So this will strongly depend how the CMEs are oriented and how they're coming towards each other. And of course, what is the background solar array? That plays a big role. No unified picture, I'm afraid.
And I agree with Julie, it's really good to understand the simple case. We need to do that, but we also need to be aware of these other possibilities that are happening, especially if we want to predict what's happening.
Okay, so at this point, well, first I'll make a comment that Olga has commented that Noé Lugas did a lot of work on CME interactions. She provided a link to his 2017 solar physics paper. I'm going to ask the people in line to wait, and we're going to have our panel discussion and come back because I'm sure you can get them to respond as well. And you guys can also pitch in and come to the mic if you have a direct response, but we do need to switch to the modeling panel. So